Hi, everybody. Okay, so I hope you can hear me. I'm not going to have video today, but I wanted to go through the second part of the analysis of variance lecture that we started on Tuesday. So if you remember on Tuesday, we went over the theoretical part of analysis of variance, or ANOVA, and that would include the different components of analysis of variance, which is the between subject differences and the within subject differences. Between subject differences is essentially a treatment effect plus chance or plus error, and the within treatment difference would be the actual error, okay? Or how much error to expect between mean differences that's due just by chance, right? We talked about the F ratio and the characteristics of the F ratio, which include that it has a positively skewed distribution. We talked about why that is. We discussed the null hypothesis, and that it is 1 instead of 0, and why that is. And so we did a little exercise together and went through the answers, and now we're going to jump into the hypothesis test with the analysis of variance and the test statistic of the F ratio. Okay, so for this lecture, you're going to need PowerPoints. These PowerPoints, maybe probably the other ones as well. Your F ratio table. F ratio table is in the PDF file tables, and it's just one page, and it literally says like F distribution table at the top. So I know I've attached those several times to different announcements. So you just need to make sure you have that in front of you or pull that up on your computer. And then the practice worksheet that I have included in the announcement as well. Okay, so first things first, we state our hypotheses in any hypothesis test. There's a few differences, as you might see if you've looked at this already. So the null hypothesis for an analysis of variance is mu1 equals mu2 equals mu3. If you remember that if we just had two means, okay, that would be like a two sample or independent sample t-test. So mu1 equals mu2. But since analysis of variance allows us to have two or more means, then we are, we're gonna write however many means we want. So so the null hypothesis would be no differences among or between any of the means, right? So if we had 10 means or 10 treatment groups, mean 1 of the first treatment group equals mean 2 of the second treatment group equals mean 3 of the third treatment group equals mu 4 of the fourth treatment group, on and on and on. Okay, so in the case, in the situation that we looked at, the data that we looked at, temperature has no effect on performance. So if you bring up your the worksheet that I gave you, you should be able to, let's see if I can do that. All right, so this worksheet, oh, okay. So anyway, I can't get it at the moment, but the worksheet that I attached, the first part should be all of the data. And from Tuesday, in the lecture on Tuesday, we had that same table with the same data. You can also look at the PowerPoints from Tuesday, all of that stuff. It all has the same data set. And the data set has the factor temperature, and it has 3 levels of the factor, which are a 50-degree room, a 70-degree room, and a 90-degree room. So make sure that you have that in front of you. Actually, it's very important that you have it in front of you, because as we go through the hypothesis test, you're going to refer to those data quite often. All right, so if you need to pause, pause, make sure you have it. Okay, so our null hypothesis is that there is no effect on performance. And performance, I guess, we would probably just measure it by test scores, right? So does temperature have an effect on test scores or performance if we're talking about academic performance? So for the alternative hypothesis, we are just going to write at least one mean is significantly different from another. Sorry. And so why do we say it like this? Because as amateur researchers, we are uncertain which mean differences we predict are the same or different. So for example, if we wrote out our alternative hypothesis in the same way as we normally have, it could look something like this. Mean 1, the first treatment group might be equal to mean 2 of the second treatment group. Sorry, the mean from the second treatment group, but the mean from the second treatment group may not be equal to the mean of the third treatment group, and so on and so forth. So we really don't know, at least from where we're at, right, as stats students, we don't know this research, or whatever research we're looking at in the real world. So because of that, we're just going to say at least one mean is significantly different from another. It's way too much to write down all the possible combinations. We're just going to make it simple. Okay. Okay. So the second thing we're going to do is find the critical region. So just ignore over there. So here's the thing. Okay, so find the critical region. So first of all, we're going to need, I want you to get out your F table. So make sure you have that out. Your degrees of freedom has two calculations with it. So we have sum of squares calculation, we have degrees of freedom calculation, and then we have mean square or variance calculations. So before we even get to all the calculations, you are going to have to calculate degrees of freedom. So we're calculating the degrees of freedom within each group, and we're calculating the degrees of freedom between each group. So in order to do that, here are the formulas. So to calculate the degrees of freedom within each group, we're just going to sum up the degrees of freedom for each group. Okay, so the summation value, and we're going to add up all the degrees of freedom. So in other words, it'll look like this, and the n from the first treatment group minus 1, plus the n from the second treatment group minus 1, plus the n from the third treatment group minus 1. And if you add all of those up, you're going to get 12. So 12 is our within degrees of freedom within value for this data set. So then we have to calculate our degrees of freedom between, which is simply k minus 1. And if you remember that k stands for the number of levels of the factor. So in other words, the number of treatment groups. In this case, we have 3 treatment groups minus 1, and then that would be 2. So our degrees of freedom between is 2. Okay, so once we have the within degrees of freedom, 12, and the degrees of freedom between, just 2, then we need to consult our F table. So our F table will always set in alpha a 0.05. Okay, and here's the thing with the F table. So you'll notice that degrees of freedom go on the left side of the table, right? They're listed. And then on the first row, we have degrees of freedom in the numerator. Okay, and here we have degrees of freedom in the denominator. So what does that mean? Well, degrees of freedom in the denominator is going to be the within degrees of freedom value, because the denominator is always the same as within group differences. If you remember the last lecture, we talked about within is the same as error, okay, which is error is always in the denominator. So this is within treatment groups within degrees of freedom within. So we ended up with 12 for degrees of freedom within, and so 12 is what we have here. For the numerator, I just wrote between up here just so that I remember that degrees of freedom numerator is degrees of freedom between. So this is why we had to do these calculations first. So degrees of freedom between is 2. We already calculated that. So we're going to find 2, and then we're going to go meet where they meet, and there's 2 values. Now, on your F table, you should see that the value that's in bold at the bottom is the when you set the alpha of 0.01. The value at the top is when you set the alpha of 0.05. And unfortunately, sometimes when the F table gets printed out or copied, it doesn't actually show the boldface versus the lightface type. So just in case that it doesn't show for you, I just wanted to make sure you knew that it's the top number for each pair that is that we can find an alpha of 0.05. So kind of highlighted all of the correct critical values here. And again, notice they're at the very top of the, the 2 pairs for, I'm sorry, the pair for the critical value. Okay, so hopefully I made that a little more clear. So our critical value, let's go back up here. So our critical value is 3.88. So if we find 3.88, of course we have a positively skewed distribution, so it's going to be a positive number, and we hope that the F ratio is as far right from 1 as possible. Why is that? Because 1 is now our null hypothesis. So when we have an F value that's close to 1, it's more likely that we're going to retain the null hypothesis, which is of course what we don't want to do. So the further out, the larger the F ratio is, the better. And in this case, our critical value is 3.88. So we hope that our final F ratio that we get after our calculations is going to fall in this critical region somewhere. Okay. Okay, so now for the calculations. So there are 9 calculations for the F ratio itself. And then of course, we're going to have one effect size to calculate, but that's nothing that you haven't done before. So for this part, I'm going to have you bring up, of course, again, your F ratio table, and then the F ratio calculation document. And this is attached to the announcement. So I'm going to give you a second to pull that up. Okay, so this is what you should have. There's 2 pages. You have the data, and this is what I've been referring to so far, and this is what we looked at last lecture. And then I have the calculation steps. Okay, so first of all, just to reiterate, we have the temperature conditions, which is our factor. We have 3 levels of the factor because we have 3 treatment groups. 1 at 50 degrees, 1 at 70 degrees, and 1 at 90 degrees. So we've put an N of 5 people in each group, okay? And we've given them, we've probably taught them something and then given them a test in whatever we taught them in. And we want to see if there is an effect of temperature, okay, on their test scores. So we're hoping that there's significant differences between or among these means, and if there is, we're more likely that there is an effect on their scores and more likely to reject the null hypothesis. Okay, so just as another quick review. So remember, we divide our analysis of variance sort of into more parts. So we are actually allowing for more, to control for more error. So in this case, our between treatment differences are going to be group 1, group 2, and group 3. So are there differences between these two, differences between these two, differences between these two? If we have at least one difference, we're going to say that we reject the null hypothesis, okay? So that's between group differences. Our within group differences is literally just the variability within each group. So this group scored 0, 1, 3, 1, 0. Is there variability and how much? This group scored 4, 3, 6, 3, 4. Is there variability and how much? And this group scored 1, 2, 2, 0, 0. Is there variability and how much? So forgetting all this other stuff for now, the mean for each group has been calculated down here, and even we see that there's mean differences, but we of course have to conduct the hypothesis to find out if they're significant. Okay, so these are the data that I've been referring to and I will continue referring to when we look at the calculations. Okay, so here are the steps for the calculations. Now, what I'm just going to point out are the actual formulas. And I'm not going to point out how I got the formulas. I'm sorry, and how I get the values, because I feel like if you, once we have the calculations, okay, the formulas, excuse me, then it should be pretty simple to plug those in and calculate the actual values that are being asked for, okay? So you're gonna have to keep referring back to this guy, all right? Okay, so our formulas are divided as such. We have sum of squares formulas. We have degrees of freedom formulas, and then we have mean square formulas, which is the same thing as variance. And then all of that stuff is going to come to equal the F ratio, okay? So we have sum of squares, 1, 2, 3 formulas, degrees of freedom, 1, 2, 3 formulas, and mean square, we have 2 formulas, and then our final F ratio. So that should be 9 different different formulas, but when we break them up into the different pieces, it's not going to seem like that. Okay, so for our sum of squares part, so we're going to take the sum of squares total. That's the first formula. So sum of squares total. The formula is a squared score summed minus g squared, which is a grand total, divided by n. So if you look up here, okay, you can see the squared score summed is 106. Our grand total, or our g, is 30. We square that. We divide g squared divided by 15. So of course we want to do the division first and then add the other value. So that's what we did here, right? So we did, oh, sorry, this should be a 2 superscript. So 30 superscript, right, divided by 15 is going to give us 106 minus 60, which is going to give us 46. So our sum of squares total is 46. Okay, so then our next formula is the sum of squares within subject differences. So this is the error. Okay, so the sum of squares within treatment, the formula is the sum of squares for each treatment group, and just add those up. So if you look back up here, the sum of squares is 6, 6, and 4. So if we just add those up, we'll get 16, and that's it. And then our sum of squares for between is our sum of squares total minus the sum of squares within. Well, guess what? You already have the total, you already have within, so you're just going to simply subtract those, and you'll get 30. So you have values now. The first 3 formulas are done. And guess what? You've already done degrees of freedom and degrees of between when you were trying to find the critical value using your F ratio table. So we have those values here already. we just have to calculate the degrees of freedom total, which is the total N of the entire study minus 1. So if you count up all of the numbers of each participant or each score, you have 15 minus 1 equals 14. So here are all the scores or the values for the degrees of freedom, total, within, and between. The mean square, so we're getting close. The mean square is also considered the variance, and this is just in analysis of variance. So the mean square within divided by the degrees of freedom within, so we have variance here, right? Sum of squares over degrees of freedom, 16 over 12 is 1.33. And then we're going to find our mean square between. And our mean square between is sum of squares between divided by degrees of freedom between, which is 30 divided by 2, which is going to give us 15. Okay, so 30 up here. Oop, if you go up here. Okay, so sum of squares between divided by the sum of squares within. Sorry. Sum of squares between divided by the degrees of freedom between, okay, which is 2. So 30 divided by 2 is 15, and that's your mean square variance, which is variance between treatment groups. So the mean square between is 15, mean square within was 1.33, and so our F ratio becomes 11.28. Okay, and if you need to go back and listen to that again, that is very advisable. If you want to go back and look at those again, that's also very advisable. And then of course we can clarify all of this on Tuesday. Right, so let's go back to, oops, open. All right, so let's go back to our decisions. We have all of our values except one last thing, right? We do need to calculate the effect size for the F ratio. So the only effect size that I'm concerned about is the eta squared. Some of you have already looked at that and it says n squared. There's actually the Greek letter eta squared. And so the formula for that is a sum of squares between divided by the sum of squares total. Guess what? You already have all of that information on your table. So if you take those numbers and divide them, you'll have 0.65. So your eta squared is 0.65. Now remember that the formula for this particular effect size is the same as R squared, by the way. The percent of variance accounted for by our treatment. So in other words, our treatment in the temperature, okay, accounted for 65% of the effect on test scores, right? And so what that means, that's actually a really big effect size in behavioral science statistics. In fact, in behavioral science statistics, if you have a 0.14 or 14% R squared or eta squared, that is considered very large, okay? So 65% is sort of unheard of, but still possible. So anyway, just a little aside. So what is our decision? So we're going to reject the null hypothesis because 11.28 falls well beyond, well to the right of 1. It's much larger than 1. We're going to say that the temperature has a significant effect on test scores, and here's how we write out those statistical values. So our F ratio equals 11.28. But notice, kind of like the t-test, we have to write in the degrees of freedom. But because we've taken in an account 2 degrees of freedom, which is 3, the degrees of freedom between, and 12, the degrees of freedom within, we have to make sure both of those are in the parentheses. So our p-value is less than 0.05 because we actually had less than a probability of committing a type 1 error, and our eta squared is 0.65. And so that is what you need. Now that is the decision that you make regarding the null hypothesis, and that's exactly what we're hoping for. We have a very big effect size and a very large F, so it makes sense that we are going to find a treatment effect. Okay, so I'm going to provide you some practice problems. I've attached that to the announcement. Because we're going to go over those in class on Tuesday, I want you to use a pencil or another sheet of paper because you're probably going to have to make some adjustments, right? But I want you just to kind of on your own, using the example we just looked at, attempt to go through step 1, step 2, step 3, and step 4 of the hypothesis test, and do your best to complete those in pencil. And then we can, like I said, we'll go over some of the answers and clarify more of that on Tuesday. So feel free to ask. Let me know if you have any questions, and this will be posted shortly as soon as I can upload it. And I hope you all have a good weekend. Stay safe and be well.